In this lecture video, we are going to take a look at types of chemical bonds. Please read the OER textbook chapter 5.1 for more details. The homework that associated with this is the Newton Homework 5.1. Let's take a look at the additional handout. This slide right here can be found in the additional handout at the end of your lecture manual. Please turn all the way to the end of your lecture manual to see the additional handout section, and you will find this slide right here. So pretty much before we talk about the chemical bonds, we will need to know first that the most stable electron configuration can be found for the group of the noble gases. So pretty much noble gases already have the stable electron configuration, therefore they are most likely to stay isolated. They are going to present as one single atom in nature, and they do not want to form bonds or share any electron or transfer any electron with any other atom. So in this case, pretty much when we talk about the rest of the element, those are what we are going to focus on when we talk about the chemical bonds, okay? Because these elements are going to form groups of atoms, or sometimes they are going to form molecules or compound. At the end of this lecture, you are going to see the difference between group of atoms, molecules, and compounds. Okay, so pretty much what we are going to take a look at when we talk about chemical bonds, we are going to focus on everything else except the noble gases, because in nature, noble gases of this element here are going to present as an isolated atom in nature. Here is the overview of the types of chemical bonds. Let's start with metallic bonding. Metallic bonding present in the combination between metal and metal. It can be metal of the same element, such as sodium atom, right? So several sodium atom grouped together. The type of bond that hold these atoms together is what is called metallic bonding. Or sometimes it can be metal of the different element as well, and those are different element metal atoms are going to mix together, form a mixture called alloy. Okay, so we are going to take a look at that in more detail later on in this video. The characteristic of the bond for metallic bonding is that the electron are going to stay as a pool or in a sea of an electron. Okay, so sometimes we call this electron pool or sea, electron sea model. And the electron is going to freely move around this metallic bonding. That's the term delocalize means, right? So electron can delocalize or can move freely over the entire metal, right? So over that. Okay, so this electron delocalization is what responsible for the characteristic of metallic compound, such as they are good conductor for heat, electricity, and they are able to be powered and drawn without breaking as well. So we're going to take a look at this in more detail later in this video. Okay, so pretty much the metallic bonding are present in the metal sample. So any of these metal sample, right? So any of these metal element, and again, sometimes it can be the same element, or sometimes it can be of the mixture of the different metal element. Okay, so those are called alloy, right? So we're going to take a look at that also. Okay, the second type of bond that we're going to take a look at is called ionic bonds. Okay, ionic bond is present in the combination between metal and non-metal in a fixed ratio. The characteristic of this type of bond is that the electron would completely transfer from metal to non-metal. Okay, so we're going to take a look at also why later when we talk about the ionic bond formation later on. The fact that the electron completely transfer is going to create cation and anion. The cation and anion in ionic compound are held together by electrostatic force, which is the attractive force between the cation and anion, which is a very strong force, and that is what responsible for their characteristic of ionic bond, such as that they are going to be solid, and also they are going to be in crystalline lattice, and they are going to have high melting point and boiling point as well, because of the force that hold them strong. So an example of this would be, for example, table salt, right? So when you have sodium and chlorine, you have metal and non-metal, the electron would transfer from metal to non-metal. Okay, so creating ions that hold together by electrostatic force. Okay, and they are most likely to be found in a crystalline lattice like this. Okay, so here are the combination for the ionic compound, right? So we have majority of metal, any of these metal, when they combine or react with any of these non-metal, you are going to end up with ionic compound. Okay, so the formation of ionic compound generally can be explained by the electron shell model that we learned from the previous lecture video. For example, between magnesium and oxygen here, magnesium contains 12 proton and 12 neutron, and therefore it contains 12 electron as well. So in this case, because the outer shell electron, which is the valence electron, there are only 2. In order to make this magnesium to have a stable electron configuration, it needs to have 8 valence electrons. So it either can accept 6 more, or it can either get rid of these 2 to have 8 for the as the inner shell, right? So it can do either one. So the most preferable process would be losing 2 because it's probably easier than gaining 6 more. Okay, so same thing for oxygen as well. So gaining 2 more probably easier than losing off these 6 in order to have 2 electron in the inner shell, which is going to equal to helium, right? So 2 electron equal to helium. So that would be a stable electron configuration too, but it's unlikely to lose all 6 of them, right? Because you have 6 electron. Every time you lose electron, you already see in the ionization process that it requires a lot of energy to remove every electron. So in this case, it's most likely to actually gain 2. So the 2 electron would come from magnesium to oxygen. So that means if you have magnesium and oxygen together, magnesium is going to most likely to give up those 2 electrons to oxygen in order to achieve the octet, right? So octet means 8. Okay, so the octet valence electron, which is the same as the noble gases. And once the neutral magnesium atom lost 2 electron, is going to become magnesium 2 plus. Okay, because electron have negative charge. So losing 2 negatively charged particle is going to become positive, right? And because oxygen are gaining 2 more electron, therefore oxygen would become oxygen 2 minus in this case. So this is the main reason why when we talk about the periodic table earlier, you are able to predict the main group element charges because we know exactly like how many electron for the valence electron are for each group, right? And how many they have to gain or lose in order to achieve the noble gas electron configuration. So in this case, those charges are come from that, right? So note that when we talk about the size of the cation and anion earlier, when a neutral atom become cation, the size would get smaller, right? Because you minimize the electron repulsion, and also in this case, you actually get rid of the energy shell as well, right? For oxygen, the size of the anion for oxygen would get bigger because as oxygen, neutral oxygen accept 2 electron is going to the electron repulsion would increase, therefore electron would stay a little bit further away from each other, so therefore it's going to make the size of the ions a little bit bigger, right, when you measure the distance from the nucleus to the outer shell. Okay, so again, so this is what we refer as ionic bond when the electron transfer completely. Okay, so in this case, what we are going to end up having you are going to end up having the cation and anion attract by each other through the electrostatic force between positive and negative charge. Okay, so the last type that we are going to take a look at is covalent bonds. Okay, covalent bonds are present in the combination between nonmetal and nonmetal in a fixed ratio. Okay, so the characteristic of this type bond is called electron shared. The electron would not transfer completely, but they are going to share between the element or between atoms. Okay, so the sharing type of bond is going to be what is responsible for the characteristic of the covalent bonds, okay, so or the covalent compound. Another name of the covalent compound is called molecular compound. Okay, so molecular compound or covalent compound, they are the same. Okay, so they describe the same type of bond and they describe the same type of compound. Okay, so this type of compound right here, the reason why we call molecular, because they are pretty much stay as a molecule. We're gonna take a look at each individual molecule. Okay, so I'm going to talk about why don't we call ionic compound as molecule later when we've actually focuses on the formation of ionic bonds. Okay, so but pretty much because the electron sharing characteristic of covalent bond is going to responsible for the fact that you can find the covalent compound in several type of phases at room temperature, and they are going to have a lower melting point than the ionic compound as well. So pretty much if you compare the strength between covalent compound versus ionic compound, the covalent or molecular compound would have a weaker bond within them in comparison to ionic compound. Therefore, they are most likely to have a low melting point and also low boiling point as well. Okay, so an example of covalent bonds or covalent compounds would be the bond in water, right? So water, hydrogen, oxygen, those two are non-metal. So when they combine, they are going to form molecular compound or the bond between each of these atom within the molecule. That's what we call covalent bond. Okay, so here are an example of the element that can combine to form molecular compounds or to form the covalent bonding. Okay, so pretty much majority of it would come from non-metal mixed with non-metal, right, or react with non-metal in a fixed ratio. Sometimes you will also can see the metalloid as well that can form molecular compound. Okay, so pretty much it's come from majority of them come from non-metal and non-metal, and sometimes you can find metal and non-metal as well. Okay, so here's the formation of molecular compound. So pretty much instead of the electron transfer completely like what you see in ionic compound, they are going to share electron. For example, carbon, this is the electron shell model of carbon. Carbon has 4 valence electron, right? So 1, 2, 3, 4. Carbon doesn't have an octet yet. Octet means 8 electron outside, right? Like noble gas. So in this case, in order for carbon to have an octet, it needs 4 more electron to share, right? So that's why we are going to, if you are going to form a compound that contains hydrogen, it's going to require 4 of the hydrogen because each hydrogen atom contains just 1 electron. Okay, so in this case, 1 electron of hydrogen would come to share with the outer shell electron of carbon. So therefore, in this case, the hydrogen electron configuration would be satisfied by the fact that it's going to be the same as the number of electron as helium, right? Because if you consider hydrogen here, they already have 2 electrons, right? One is from itself, the other is sharing with the carbon. So 2 electrons, that is making hydrogen achieve the electron configuration as helium, which is stable. For carbon, it's the same thing too, because carbon already have its electron equal to 4. Once it's share electron with 4 hydrogen, total of sharing and total what is have originally is going to come out to be 8. So 8 electron in the valence shell. This is going to make carbon to achieve the stable electron configuration in this case. So therefore, when you have hydrogen and carbon come together, they are going to share electron because of that. Okay. So again, the fact that they are sharing, they're not completely transfer. This is the characteristic of the covalent bond, which is completely the opposite of the ionic bond. Now let's us take a look at the more detail of the metallic bonds that present in metals and alloys. Metals that we are going to take a look at is going to be of the same element, such as sodium metal, it would be of the sodium element. When we talk about alloys, this refers to the homogeneous mixture of 2 or more metallic elements. An example of alloys would be brass, that is the mixture between copper and zinc. Okay, so what we are going to take a look at is that pretty much we're gonna take a look at why metal form the metallic bondings. Okay, so before we do that, let's refer to the previous lecture video. In the previous lecture video, we learned about the metallic character and also we learned about the ionization energy as well. And we know that those metal elements are most likely to lose electron. The reason for that is because they are having a bigger atomic size, bigger than non-metal, right? Because they are having like less effective nuclear charge, and some of them toward this side right here is have a large energy level as well, because they are most likely to lose electron easier than the non-metal. Therefore, these metal are going to have metallic character, which means they're going to lose electron easily. Therefore, the energy that required to remove its electron would be less. That's why the first ionization energy would be low as well, right? So this is the characteristic of metal, right? So they have lower first ionization energy, and also they have a high metallic character as well. Okay, so because metal can lose electron easily, it requires less energy to remove their electron. Therefore, the electron would be removed. So it's going to create the metal ions. Okay. However, these electrons that are lost is not going to go anywhere, because nothing else is going to accept this electron, right? Because you have metal and metal and metal and metal, and those metal do not want to accept any electron. They're most likely to lose. Therefore, electron will not go anywhere else. Nothing accepted. So therefore, electron is going to travel around each of these nucleus that present in the sample. So this electron that is being lost is going to pull together, and that's what we call electron pool. And sometimes we call this sea of electrons. Okay, the electron and the metal ions are held together by electrostatic force, which is an attractive force that is strong, right? So therefore, electron will not go anywhere either. It's just going to travel around between these atoms, right, of the nucleus of these atoms. The freely moving of the electron is what we call delocalization of the electron. The delocalization of the electron allows the metal to be able to conduct heat and also to conduct the electricity as well. And is also responsible for the fact that metal can be drawn and can be powered without any breaking as well, because these electrons are going to move around, be able to spread out without breaking. Next, we are going to take a look at the melting point and boiling point of different type of metal. Okay, so before we get into that, let's take a look at what melting point and boiling point means. In order for a solid to go to liquid, it needs to go through this transition where it's going to melt, and the temperature at which it melt, that is what we call melting point. Okay, so in order for solid to melt, it need to be separate out, right, to spread out. So therefore, in this case, the force that hold the solid together need to be broken, okay, in order to spread out into the liquid state. Okay, same thing if the liquid changed into gas as well. Once liquid changing to gas, the temperature at which liquid changed to gas, that's what we refer as boiling point. Okay, so at this point, the liquid, the force that hold them together would be broken, and it's going to allow the liquid to be spread out into the gas state. So in the gas state, you will see that the force that hold them together would be the weakest compared to liquid, and then solid, the force that hold them together would be the strongest. So in this case, we can associate the transition of the state with the force that hold them together, right? For example, if the force that holds solid is strong, it's going to require higher temperature to melt. Same thing for boiling point as well. If the force that hold liquid are strong, then it's going to require higher temperature to destroy those forces in order to change from liquid to gases. So if we compare the melting point or boiling point of these three different metallic element, you will see that the melting point and boiling point increase, right, as you go from group 1 to group 2 and to group 3, right? So on the periodic table, if you're looking at this, right, sodium is in group 1A, magnesium is in group 2A, and aluminum is in group 3A. So therefore, in this case, you know that they are going to have the same number of energy shells. And because sodium is in group 1, is most likely to going to become a positive 1 ion. Magnesium would be positive 2, and aluminum would be positive 3, right? Because if they lose this electron, they are going to have the same electron configuration as the noble gas neon, right? So here are the metallic bondings that hold the metal ions together. So in sodium, it would be the electrostatic force between sodium ions and the electrons, right? And its electron. Same thing for magnesium as well. It would be magnesium ions and its electron, right? Aluminum ions and its electron. And because we have several atoms of sodium together, therefore what we are going to have is we are going to have a pool of metal ions and also a pool of electron as well. And these electrons are what we call electron pool or electron sea, right? They are delocalized, they can move freely. Okay, so why are these melting point have similar trend, right? For sodium go to magnesium and go to aluminum is always increased, right? Melting point increase as we going from sodium to aluminum. Same thing for boiling point as well. So that's what we're gonna take a look at. Okay, so note that when the charge of the ions increases, for example, from +1 to +2 to +3, the size of the ions will decreases, right? Because as it lost more and more electron, the size would shrink even further because the electron repulsion within that ions would be less. And in this case, you are having a stronger attractive force from the nucleus that have a higher effective nuclear charge as well, right? So that's why the size of ions for aluminum would be a lot smaller than sodium in this case. Therefore, because the ionic size decreased, the forces that hold them together would actually increase because in this case, the size is small. The electrons are able to stay closer together with the nucleus. And because effective nuclear charge of aluminum is higher than sodium, so that means the attractive force that hold aluminum's electron toward their aluminum ions would be a lot stronger than the attractive force between sodium ions and their electrons as well. Because the force increases, therefore in this case, for sodium to melt is going to require less energy than for aluminum to melt. Therefore, aluminum would melt at a higher temperature than sodium. Same thing for boiling point as well, because aluminum are hold together with a stronger attractive force than sodium. Therefore, if aluminum going to melt, is going to require at a higher temperature to separate these apart, right? Require more energy to separate them apart, because the force that hold them together are stronger. Therefore, in this case, we can conclude that as the attraction increases, the melting point and also boiling point will increases as well. Okay, so it's come from that. The next thing we're going to take a look at is the detail of ionic compounds. Okay, so pretty much ionic compounds are the compound that compose of metals and nonmetals, and these atoms of metal and nonmetals are held together by the ionic bonds. Okay, so which is the electrostatic force between cation and anion. Okay, so they attract each other because they are opposite charge. Okay, so the electron is going to transfer from metal to non-metal. The reason for that is because we already talked about this, right? For metal, metal has lower ionization energy than non-metal. Therefore, in this case, it's easier to remove the electron, right? Non-metal have a higher ionization energy. Okay. And because metal has lower ionization energy, therefore metal is going to be easier to remove electron or tend to lose electron. That's what the metallic character is, right? So this is have tendency to lose electron easily, which is not the same as the non-metal. And also non-metal for its having a small size and also have a high effective nuclear charge, this one is able to attract electron more as well. Therefore, they are going to have higher electronegativity also. So therefore, in this case, most likely the electron would transfer from metal to non-metal because of that, right? So in this case, electron would transfer from metal to non-metal. Okay, so an example of how to write chemical formula, chemical formula of ionic compound, you will need to actually understand first how the ion is being formed. Okay, so in this case, we are going to refer back into the periodic table that we talked about earlier, in the previous lecture video and also the electron configuration as well. So I would like you to compare between beryllium and nitrogen atom. Okay, so we're gonna take a look at what would you expect to happen to beryllium and what would you expect to happen to nitrogen if you combine these two or if you react these two together. Okay, so pretty much if you're looking at the periodic table, if you write the condensed electron configuration of these, you are going to get helium as the noble gas core electron, right? Followed by 2s2 for beryllium. Okay. For beryllium to achieve the stable electron configuration, it's going to be easier to lose these two electrons into s subshell. Okay, so to become beryllium 2 plus, because beryllium 2 plus would have the same number of electrons as helium, which is one of the stable noble gas, right? And if you look at nitrogen, for example, okay, so if you draw the electron configuration of nitrogen, helium would be the noble gas that come before nitrogen, right? So it followed by 2s2 and followed by 2p3. So in this case, if nitrogen going to achieve the same electron configuration as helium, it needs to lose 5 electrons, right? So, and we already mentioned that every time when you lose an electron, right, according to the successive ionization, it requires energy every time we remove electron. Therefore, in this case, it's harder to remove 5 of them, right? It's easier to remove just 2. Okay, to remove 5 is a lot harder, but to accept 2 is easier. So that, accept 3 is easier. Why is have to accept 3? Well, because 2p right now contain only 3 electrons in the 3 orbital of 2p. To add 3 more, the 2p would become 2p6. So that would be the same as electron configuration as neon. Okay, so this is going to be the same as neon. So therefore, in this case, accepting 3 more for nitrogen would be easier than losing 5 to achieve the neon electron configuration. Okay, so that means pretty much in this case, when we are looking at ionic compound, we are going to keep this in mind that which one is going to gain or which one is going to lose is going to depend on which direction it's easier to achieve the electron configuration as the noble gases. Okay, so that's what we are going to take a look at. Okay, so for example, if you react sodium with chlorine, right, most likely sodium going to give up its electron to chlorine, and chlorine would be able to accept it, because for sodium to lose, it's just lose 1. For chlorine to accept, it's only just have to accept 1, right? So therefore, in this case, sodium, which is the metal, would become cation, and chlorine, when it's accept electron, it will become anion. Okay, so these ions that form, they are going to attract each other in 3 dimensions to form the crystallized structure like this. Okay, so that's why whenever that you see ionic compound, they are going to be present as the salt form, which is in the crystallized form like this, right? So this is an example of table salt. Okay, because of these ions are going to attract to their neighboring ion as well, because they are ions, right? So they are going to attract by electrostatic forces. Okay, oops, sorry. So as I mentioned earlier, right? So whenever that you see metal and non-metal combine, right? Metal and non-metal combine, these are going to be an example of ionic compounds. Okay, so all of these ionic compounds are held together by electrostatic force between cation and anion. Okay, in 3 dimensions. So that's why all these example of ionic compound, you will see all of them are going to be present in the crystalline lattice or crystallized structure, and they are going to have a high melting point as well, because the electrostatic force is a very, very strong force. In order to make these melt, it's going to require a high temperature to separate the charges away from each other, right? Because positive and negative attract each other, so to separate them is going to require a lot of energy for that. Right, so that's why you will see the melting point are really high. Okay, so if you're looking at different group though, sodium and potassium are in the same group, right? So sodium is smaller than potassium. You will see that the melting point of the smaller ions, right, going to be higher than the melting point of the bigger ions as well, right? Potassium and sodium here. And if you compare the charges, right, between sodium and magnesium, you will see that magnesium 2 plus, sodium is 1 plus. So in this case, you will see that as the charges increase, the melting point also increase as well, which is similar to the metallic bonding that we just discussed earlier, right? So as the charges increase, right, from +1 to +2, you will see that the melting point increase significantly, which is indicate that these are held together by a stronger electrostatic force than these two, right? So that's what it means. Okay, so the next thing we're going to take a look at is we're going to take a look at how the ionic bonding is being formed and what are the energies that is going to associate with this. We are going to tie back into the previous chapter section video that we talk about different type of energies like ionization energy, electron affinity and things like that. We're going to tie that back here. First thing I want you to actually write down is the enthalpy. Okay, so note that enthalpy is the heat of the reaction. Okay, so it's pretty much enthalpy is the heat of reaction. You are going to see this term again, heat of reaction, when you are taking 122. Okay, so pretty much this is referred to the heat involved with the chemical reaction. Okay, so what we are going to take a look at is we're going to take a look at the formation of table salt from sodium and chlorine. Okay, so sodium in nature present as the sodium metal, which is solid. Okay, so this is solid right here, is held together by electron pool, right, or what we call metallic bonds. Okay, so that means in this case for sodium, in order for it to lose electron, it will not lose it directly because it need to go into gas phase first, right? So first it need to melt, then after it's melt, it need to boil, right? So, and you see that in order for sodium solid to melt and eventually to boil, you are going to keep adding heat to it, right? Because from what we see earlier, those are like the melting point and boiling point of sodium are very high, right? So that means we are going to have to input the energy or input heat for this, for sodium to melt and then to boil into gas state. Why do we need to do that? Okay, so we're going to take a look at the next step, why. Okay, so pretty much the energy or the heat associated with this process for sodium to melt and then to go to gas, right? So in this case, so for sodium to melt, for sodium to melt and for sodium to boil, right, to go to gas, the energy that required for this is 107. You don't need to know this amount, okay, but know that this process is going to require energy. Okay, so this process requires energy. That's why the energy is positive, because this process indicates endothermic. Okay, because it's going to require this much. Okay, so that's what you know, this process is endothermic. Now, once sodium becomes gas, sodium in gaseous state can lose its electron like completely. This process is what we call ionization process. Okay, so it's going to require significantly amount of energy to completely remove electron. Okay, so the first one that we see, the electron is not fully removed because the electrons are held together in the metallic bonding, right, as the electron pool. But to remove those electrons completely is going to require a lot of energy for that. Okay, so and this energy is what we refer as the first ionization energy, where we remove its first electron. You learn how to write out these equation already, and this is what my expectation is. You will need to be able to write out the equation that associated with the first ionization energy. Okay, so the first ionization energy is the energy that involved with the gaseous element, right, loses electron and become the cation in gaseous state. Okay. Second thing we are going to take an account for is the second element, which is chlorine. In nature, chlorine is present as molecules Cl2. We are going to take a look at this later when we talk about covalent bond. But note that when we are forming sodium chloride, we just want only one atom of chlorine, right? Because sodium chloride and ACl, we need just one chlorine. But in nature, we have two atoms of chlorine held together by covalent bond, which we are going to take a look at later in this video. Therefore, in this case, we need to break this bond first. Okay, so that means we're gonna have to divide this by half or break it, right, in order for us to obtain only one single chlorine atom in gas state. Okay, and the amount of energy that required to separate or break the bond of chlorine gas to atomic chlorine here is going to be this amount, right? This much. Again, you don't need to know the number for this. What you need to know is that all of these processes are endothermic. Okay, so up to here, they are endothermic, which means that it requires energy for each of these steps to happen. Okay, so it's require heat for each of these steps to happen. Then what next then? Okay, so the next thing that would happen would be this chlorine gas right here that we just break from the chlorine molecule is going to then accept electron, right, from this process right here, because sodium lost electron through the ionization energy. Therefore, the chlorine that floating around is going to accept that electron, right? Electron will not go anywhere. It have to go to another species, have to be transferred. And then chlorine neutral atom would become chlorine minus. Okay, so are you familiar with this process at all? Gaseous atom accept electron and become an ion. The process is opposite of ionization energy, that is electron affinity, right? So that means electron affinity is the energy associated with the atom accepting electron. So therefore, in this case, as chlorine accept electron, the energy associated with this is what is called the first electron affinity. And this process, when chlorine accept electron, okay, so the nucleus of the chlorine would attract to the electron, is going to be a favorable process, which means that there is indicate the attraction force between the electron to the nucleus of the atom. Therefore, it's going to give off energy. That's why, as you see here, it's giving off a negative sign. Okay, so the negative side tells us that this process is exothermic. Okay, which means that this process will happen, and in order for it to happen, it needs to release heat with this amount. Okay. Next, what we have is that we have sodium from the second step here, sodium ions that we have not used yet, right? And we have the chlorine ion that is generated from the previous step. So these two can combine, right? Sodium ions and chloride ions can combine. And once they combine, they are going to form sodium chloride solid. And this process, when the positive and negative come together, they have a very strong attractive force between each other. Therefore, it's going to give off tons of energy. Okay, so it's negative 787. And this is what we call lattice energy again. So the negative tell us that this process is exothermic. It means that it indicates the strong attraction between the two ions. Okay, so the energy that associated with the formation of the solid table salt, this energy is what we call lattice energy. Okay, so the energy associated with forming the crystallized lattice. Okay. So if you're looking at this, okay, so what is the lattice energy exactly? So pretty much when you have sodium ions and chloride ions, right? So we have a bunch of them because in one sample you have many atoms of it, right? So when you are forming the cation and anion of sodium and chloride, once they come together, right? So once they are electrostatically attract by each other, they are going to, this gaseous ion will coalesce. Okay, so which is going to emit heat eventually, and this amount of energy, or the energy that is the heat that is being emitted, that's what referred as the lattice energy. Okay, so the overall process of this, right? So if you take into account the fact that we have endothermic that require energy, and we also have this part which are exothermic as well, that is actually giving off energy. So if you looking at these two sides, right, so the amount that is consumed and the amount that is giving off, the difference between these two is what we are going to have left as the overall heat of the energy, right? So the enthalpy or the heat of reaction for this process would be the difference between these two sides, right? So it's come out to be like around 400, negative 400, which indicates that if you are going to form sodium chloride from sodium metal and chlorine gas, you are going to see the heat is being generated this much. Okay, so the overall reaction for this is, if you combine all of these together and start to cancel each of those processes, right? The overall what is happening as the overall equation is going to be sodium solid, right, react with half of chlorine molecule, and that's going to generate sodium chloride. Again, this reaction is the overall reaction. It doesn't tell you about the step of the process. These are the steps that happen throughout the whole reaction. Okay, this is the overall. And after this whole thing happen, the overall is going to give off this much of energy. And as you see here, those energy that we see, right, negative 400 kilojoule per mole, this is what we are going to observe as like light and heat that is being generated as you mix sodium metal and chlorine gas together. Is going to give a very highly exothermic reaction, which is going to produce tons of heat and also tons of light as well. And eventually the table salt, the crystallized structure of table salt would form because of that. All right, so now let's take a look at more detail of the lattice energy. Okay, so again, so to summarize of what I said earlier, right, so lattice energy is the energy associated with the formation of the crystalline lattice of the alternating cation and anions from the gaseous ions. Right, we already saw that, for example, sodium and chloride ions. And the ionic bonding is electrostatic force. So therefore, in this case, the lattice energy is going to be directly proportional to the charge and also inversely proportional to the distance. Okay, so because electrostatic force is actually depend on charge and also depend on the distance as well, right? So in this case, when we talk about energy, I'm going to use E. Okay, so force is F, right? So in this case, we are talking about the lattice energy, so I'm going to use E. So pretty much you can calculate this E by having a constant, it's called Coulomb constant, right? Multiplied by the charges, the two charges, and then divide by R, which is the distance of the two charges. Okay, so again, E is referred to the electrostatic energy, and then K is the constant, and then the Q are the charges of the two particles, and R is the distance. So think about this: if you have charges are the same charges, the same type of charges, you are going to end up with a positive energy, right? If you have the opposite charges, you are going to end up with a negative energy. The negative energy represents the attractive force or the exothermic. Okay, so the positive energy would represent the repulsion or endothermic. Because if you think about it, right, so if you have positive and positive, they're gonna repel. Therefore, in order for you to push them together, it's going to require energy to do that. Vice versa, if you have the two opposite charges, they are going to attract each other, right? They are going to give off energy, which is going to be exothermic. So that means if you are going to separate them, it's going to require that amount of energy, right? Because they are more likely to attract each other than to be separate out. Okay, my expectation for this is not for you to actually calculate the energy for this, but my expectation for you is to know the relationship between the energy, the two charges particle, and also the distance as well. What happened if you increase or decrease the distance? What happened to the energy? If you increase or decrease charges, what happened to the energy, right? So that's what we're going to take a look at. Okay, so let's take a look at the effect of ion size. Okay, so the size of ions in the trends of the lattice energy. Okay, so keep in mind that the lattice energy is going to be inversely proportional to the size, right, which is the distance between two ions. So here are the ions that have the same charges. Okay, so that's why the reason why I have to keep the charges constant, because we need to have only one unknown variable right now, so we have to control these two, right? So that way we can see one effect at a time. Okay, so if I want to talk about the size, then I have to keep the charges the same. So that's why the charges for all of these are the same, right? Positive 1 minus 1, like plus 1 minus 1 plus 1 minus 1 plus 1 minus 1. The charges of all these are the same. The only difference that we have between these ionic compound are the distance between cation and anion, right? So going from smallest to the biggest, right? So this is the biggest ion size to the smallest ion size. If you compare their energy, the lattice energy, you will see that if you ignore the negative side, okay, so you're going to see that the magnitude is going to decreases as the size increases. Okay, so or on the other hand, right, as if I if I say what I just write here, is that the magnitude would increase it as the size decreases. The reason for that is because, as we see, right, the distance is inversely proportional to the energy. The longer the distance between the two ions is going to have a lower energy, right? So that's what it means, which means that these two, if we ignore the negative side, okay, so it can mean two ways. Okay, so the first way is that the 657 tell us that if you combine cesium ions and chlorine ion together, this is going to be the amount, the negative 657 would be the amount that is going to generate. Okay, same thing for lithium and chloride as well. If you interact these together, the amount of energy that is going to be given off would be 834, which is tell us that this has a stronger attraction force than this one. Okay, so these two smaller one have a stronger attraction force than these two big one. Okay. On the other hand, if you ignore the negative side, what you can say is that if you already have the ions between lithium and chlorine, if you want to separate this, the amount of energy to separate this is going to be 834, right? Same thing for this. If you want to separate this, the amount of energy that required would be 657. So that means the magnitude of the lattice energy can go both ways. It can talk about how much energy is going to be given off or how much the energy is required to separate them, right? So the side would be the opposite for that. But for the amount of energy that producing when they attract each other is going to be this negative. So that means if I stick with one way, for example, stick with the way of the formation of the lattice energy, I can say that the more exothermic, right, so which is including the negative side, or the more negative value, you are going to see that those are the compound that contain the small size of ions. Okay, because they exhibit a stronger attractive force between the two ions. Okay, and you will see that those that are less exothermic or less negative, they are going to have a bigger size of the ions, which is going to indicate a weaker attraction between the two ions. Okay, so that's what we see here. The next thing we're going to take a look at is the effect of the ion charges, which is the Q. Okay. That have on the lattice energy. Okay, so in this case, what we are going to keep constant would be the distance, right? So that's why you see that these two are about the same, 231, 239, they are about the same size. The difference is going to be the two charges. Okay, so we have sodium plus, fluoride minus, we have calcium 2 plus, and oxygen 2 plus, right? So the charges are different, but the size are the same. Okay, so if you're looking at this, we see that clearly, right? The one that have a bigger charges have higher lattice energy, indicating that these have a stronger attractive force between the two, which makes sense because if you're looking at it, right, energy is directly proportional to charges. If the charges are high, right, so if these two are high, you are going to end up with a large value of the lattice energy as well. So that's why we have a huge value of lattice energy, and the negative value tell us that this is going to be attractive force between these two, right, because you have a positive and negative multiplied by each other, right? So in this case, we can conclude that the magnitude increases as the ion charges increase, right, because the bigger charges, they are going to attract with each other stronger than smaller charges. Okay, so we can also say as well that it's more exothermic, right, or more negative as the charges of the ions increases. Okay, so that would be the effect of the lattice energy in the formation of the ionic compounds. Okay, so one is the distance or the ion size, the other one is the charges. Okay, so let's take a look at example. Okay, so that way you actually understand this a little bit better. So if I ask you to rank, right, in terms of increasing magnitude of lattice energy, or in this case, we can look at as like more exothermic as well, right? So increasing magnitude mean it's going to be more exothermic, or sometimes it can be more negative as well. Okay, so magnitude, we are looking at the value. Okay, so we are going to look at more exothermic in this case. How can we do that? Okay, so pretty much what we are going to rank is we're going to rank it from lowest magnitude to the highest magnitude of the lattice energy. So we know that according to the Coulomb equation, we know that the one that have less magnitude of lattice energy would be the one that have less attraction between the two ions, right? The one that have highest magnitude would be the one that have the most attraction between the two ions. So in this case, you will need to look at two things, okay? So the first thing that we're looking at earlier, first one is the ion size, right? So we're looking at ion size. Second one, we're looking at ion charges. Okay, so we're looking at this before. Okay, so we already see this before. But if you go back here to the previous one, okay, you will see that the ions charge has a bigger effect, right? So it's jumping from 900 to 3000. The ion charges have higher effect than the size of the ions, right? Because if you're looking at this, when the size increase, right, the lattice energy, yes, is changed, but it's slightly changed. It doesn't change significantly like what we see the effect of the charge, right? So that means the effect of the size is actually less than the effect of the charge. Okay, so that's what we see here. So that means what we know from, if we want to rank this, that we are going to have to look at the effect of the charges first, okay? If they both have the same charges, then we're going to look at the size. Okay, so because the ion charges has the more effect on the lattice energy according to the previous slide, okay, than the ion size. So therefore, in this case, I'm going to go ahead identify the charges of each of those species. Calcium is in group 2A. Calcium would have 2 plus. Fluoride is in group 7A. Is going to have charges of 1 minus. You can do this by looking at the periodic table. Okay, so each group that each of these elements are located in, you can get their charges from that. Okay, so potassium group 1 would be +1, iodine group 7 would be -1. Okay, so same thing with sodium and fluoride as well. Now, what about titanium and oxygen? Okay, I never ask student to memorize this transition metal, right? So pretty much what you learn so far in terms of charges is that you are looking at the main group element, which is group 1A, 2A, 3A, all the way to 8A, right? So we're looking at all of those. But how do we know the charge of titanium? So this is when you will need to assign charge of one thing that you know first. In this case would be oxygen, right? So we know that each oxygen is -2. Okay, so when we assign the charge, we are looking at only one atom of that type of element. Similar to this, right? So fluorine, we're looking at one fluorine. One fluorine is +1. Yes, we have 2 of them. So the overall would equal to 0 because you have 2 plus, right? Plus, add to -1, but we have 2 of them. So overall, the ionic compound have to be neutral, right? So that's why all of these are neutral. Okay, neutral means 0 charge. Okay, so same thing for these two. We have titanium that add to 2 of oxygen, and each oxygen is -2. But overall, we have to have a neutral compound. So overall, it have to equal to 0. So if you solve for this, you are going to get titanium equal to +4. Okay, so that's where the charge come from, right? Because if you move this to the other side of equation, you're going to get +4. So that's what the +4 from titanium come from. Okay, so now the highest magnitude of lattice energy would indicate the strongest attraction, right? So in this case, we are going to go by the ions charge effect first, right? So we see clearly these have the highest charges, right? 4 plus and 2 minus. And that is going to follow by calcium fluoride, right? The charges are much stronger, right, for calcium fluoride than any of these. Now, between potassium iodide and sodium fluoride, these two have equal charge. Therefore, you are not able to compare their charges anymore. You need to go by size. Okay, so the size of sodium and fluorine versus the size of potassium and iodide, you will see that sodium and fluorine would have less energy shells that compared to potassium and iodide. Therefore, in this case, the one that have smaller size would have a stronger commutative force, so they are going to produce more energy, or it will have like a higher magnitude of lattice energy in this case. Okay, so the order would be this. Okay, so again, in to summarize this, you are looking at ion charges first, okay, because it have the strongest effect, and then followed by the ion size if the charges are the same. Okay, so you're gonna go by size. Okay. All right. The next characteristic of the ionic bonds is that they are going to, in solid state, they are going to fix in a fixed rigid structure, because these structures are held together by electrostatic force or Coulomb forces, right? So that's what responsible for their high melting point, also boiling point as well, and that's what responsible for their physical appearance as the crystalline structure, right? As the crystal, right? So it's because of that. So because in solid state, ionic compound are in this three-dimension rigid structure, their ions are not able to move freely. Not the same as metallic bondings, right? For metallic bondings, you have delocalized or mobile electron that can move around, that allows for conduct electricity. But in this case, it doesn't have any mobile ions. Their ions are fixed together in this rigid crystal structure. Therefore, since we don't have any free ions movement, if you stick the two electrodes into this, that is go through the power supply, right, you will see that these two electrode doesn't have any movement of an ions. Therefore, these you will see that nothing would be able to conduct electricity. Therefore, you will not see the light bulb light, right? Because of that, right? So it's the light will not lit because of there's no mobile ions to move around to allow for conduct electricity. Okay. However, if this salt right here, if the ionic compound is either dissolved in water, making aqueous solution, or as in liquid state, okay, when the ionic compound in liquid state or in aqueous solution, their ions will be able to move. The ion will not be in the fixed crystal structure like this anymore. They are going to have free ion to move around. Therefore, in this case, it's going to allow for the free movement of ion to conduct electricity, right, to carry the electrode potential from one electrode to another electrode, and creating the ability for the light bulb to be lit. Okay, so again, solid ionic compound will not conduct electricity because of the rigid structure. However, the aqueous ionic compound or liquid or melted ionic compound, they will have free ions, like free movement of ions that allow for conduct electricity. The last type of bond that we are going to take a look at is covalent bonds that present in molecular compounds which contain non-metal and non-metal, and sometimes it can be the combination of the metalloids as well. Okay, so pretty much it's on this side of the periodic table. Okay, so it's this combination right here. Okay, so as we see earlier, the covalent compound are held together by covalent bond that are coming from the sharing electron between each atoms, right? For example, carbon and each of those hydrogen, they are sharing electron in order to achieve the stable electron configuration as noble gases, right? So the sharing electron, which is the characteristic of the covalent compounds, making the covalent compound have different type of physical state at room temperature, ranging from like gas to liquid to solid, because this covalent bond that come from sharing electron is not as strong as the electrostatic force that held together by the ionic bond. And as you can see, the melting point of the covalent compound or molecular compound are much lower than of those in the ionic compounds. All right, so the next thing we're going to take a look at is the energy that associated with the covalent bond formation. Okay, so pretty much similar to the enthalpy that we talked about earlier, right? So this one can be indicated as energy, or sometimes it can be indicated as enthalpy as well, which is the heat of the reaction. Okay, so the formation of the covalent bonding is going to be less complicated compared to the ionic bond formation, because it's going to involve with just one step, and that is going to be the overlapping of the orbital of the two atoms. So what I'm going to take a look at here is the formation of the hydrogen molecule that come from two hydrogen atom. Okay, so pretty much we're going to take a look at hydrogen molecule that contain two atoms of hydrogen. So each of these atoms of hydrogen contain one electron, right? So I'm going to have one electron here, and these electrons are reside in one s orbital, right? So one s1, this is also one s1 as well. So when these two are further apart, there is no interaction, so they are separate. Okay, when you are pushing them together, or if these two atoms are brought together closer and closer and closer, what you are going to observe is that you are going to observe some interaction between the two orbital, okay, which is one s orbital. So before you pushing them together, or before the overlapping, the energy at this point will be 0 kilojoule per mole, which means that there is no interaction, there is nothing happen. But once we push these close together, the orbitals start to get closer together, and it's going to start to overlap a little bit. So the attraction will start to increase. When the attraction between the two atoms increase, the energy would drop. Okay, and once it's reached the optimal overlap between the two atoms, it's going to cause the maximum attraction between the two, and this is when the energy would be at the lowest point. The lowest point of energy where the optimal overlap is happening is going to cause the maximum attraction, and this is what we call the covalent bond, right? So the distance between the two nucleus that come together, that allow for their orbitals of the electron to overlap, we call this distance covalent bond. Okay, so again, so in this case, you are overlapping one s orbital, right, with another one s orbital. So, another one s orbital. So the overall, right, so you are going to actually creating one s and then two electron in the s orbital, because these two electrons are sharing between these two electrons here from each hydrogen atom. Okay, now what happens if we keep pushing these past or beyond the optimal overlapping? This is when the repulsion will happen, because this is where the two nucleus will get closer together. Remember, nucleus are positively charged proton reside in the nucleus, right? So therefore, in this case, the same charge will repel. So you are going to observe the significant overlap that is going to produce significant repulsion, and the energy would go up significantly, indicating this is not going to be attractive anymore. It's going to be repulsive forces that they are experiencing at this beyond the optimal overlap here. Okay, so pretty much the energy that required for, or the energy associated with the covalent bonding formation is pretty much just come from the overlapping of the orbital. Okay, so at the optimal overlap, which is at the highest attraction, that's where you are going to find the covalent bond. That's where the covalent bond is being formed. Next, we are going to associate the different bond types that we learned previously to the different in electronegativity value. So here is the table of the value of the electronegativity. So recall from the previous video, right? Electronegativity is the ability of the atom to withdraw electron toward itself, right? And because fluorine is the smallest and have the highest effective nuclear charge, so fluorine would have the highest electronegativity to be able to pull electron toward itself, right? Followed by oxygen and nitrogen. So as you see here, the non-metal would have most likely to have a higher electronegativity than the metal, right? Because the size is smaller and have higher effective nuclear charge. So that means in this case, if we are looking at the difference in how well they are able to attract electron, we should be able to use that information to help us figure out the type bond as well. And this is what we call bond polarity. So bond polarity is used to determine the characteristic of bond, whether it's ionic bond or covalent bond, right? By looking at the difference in the electronegativity value between the two atoms within the bond. Okay, so the greater the difference in the electronegativity is tell us that the bond is more polar, which means they are most likely to separate charge. Okay, so what do we mean by that? For example, if you have the two atoms that share electron that have the different in electronegativity value are from 0 to 0.4, we can conclude that the sharing electron between these two are equally, right? So they are equally or preferably share electron. They don't want to attract electron away from the other atom, right? So they are going to share equally. So this type bond that atom are shared equally, we call this pure covalent bond or non-polar covalent bond. Okay. However, if you have the difference in electronegativity greater than 0.4 to 2, okay, so it's going to indicate that the bond between the two atoms is going to be polar, but they still share, but they are sharing electron unequally. So these two are still considered to be covalent bond because they are still sharing electron. Electron has not completely transferred yet. Okay, so they are sharing, one is sharing equally, we call this non-polar covalent bond. The other one is share unequally, we call this polar covalent bond. Polar mean is going to create two different charges, right? So one that have higher ability to withdraw electron would withdraw electron from the other, creating partial negative charge. And the other that is not able to pull electron much toward itself is going to be the partial positive charge. Again, the delta sign here indicate partial. Okay, so partial mean is not completely or fully become a real charge yet, right? So this one is only is only partial. Okay, so however, if the difference in electronegativity value are greater than 2, this is when you are going to observe ionic bond, which indicate that the electron is already completely transferred. They do not share anymore at this point because the one atom has so much stronger ability to attract electron toward itself, so it's going to actually withdraw it, right? So it's withdraw electron from the other atom completely, so that means the electron from the other atom would transfer completely to the other. So you are going to observe the full charges. Okay, so these are the full charge, which is going to make them to be cation and anion in this case. Okay, so these are not cation or anion because they are still sharing electron. They are only partial charge. Okay, so these are polar bond. This is ionic bond because the electron is already completely transferred. Okay, so that's how we actually have the general guideline to determine whether something is ionic compound or covalent compound by looking at the what do you call, like the metal versus non-metal, right? So that is actually come from this. Okay, so that's general guideline is come from pretty much this different in polarity between the two atoms. Okay, so what do we mean by that? Let's take a look at example. Okay, so if you have the molecule of chlorine, okay, so chlorine held together, right? So if you're looking at the electronegativity value of the chlorine, two of them is 3. So if you find out the difference between these two, you're gonna see that the difference is equal to 0. It indicates that the atom of these two are share their electron equally. One will not pull electron toward the other that much, right? So they are sharing equally. So therefore, in this case, this is an example of non-polar covalent bond. Okay. However, if you have hydrogen and chlorine, you are going to see the difference in En value would be hydrogen is 2.1, chlorine is 3. So it's going to be 3 minus 2.1. Note that these value that I'm talking about here have to be an absolute value. Okay. So if you are using 2.1 minus 3, that's 5 too, but note that it has to be in the absolute value. Okay, so if you do this, you are going to see that the difference of the bond between hydrogen and chlorine come out to be 0.9. This indicates that the electron will share unequally between these two. And the chlorine, right, if you go back to chlorine here, chlorine has higher En value than hydrogen. Is going to tell us that chlorine is the one that is going to withdraw more electron density toward itself to creating partial negative charge, and hydrogen would be left with the partial positive charge because chlorine actually pull electron toward itself more. Okay, so it's sharing unequally in this case. So the type bond of this would be polar covalent bond. Okay. So now if you're looking at sodium chloride, the difference in En value of sodium is 0.9, chloride is 3. So if you do the same thing, 3 minus 0.9, you're going to get 2.1. So clearly this is ionic bond, right? So pretty much chlorine has a lot higher ability to withdraw electrons. So it's just withdraw the whole thing away from sodium, leaving sodium to become cation, and chlorine, after it's accepting electron, would become anion. Okay, so this is an example of ionic bond. So again, so the general guideline that we talked earlier, right? So when you have non-metal and non-metal, they are covalent bond. It's come from this idea, right? Because the difference in En value are not much compared to the ionic bond, right? So ionic bond, metal and non-metal, if you're looking at this, the difference in the En value is greatly, so therefore that's why whenever that you see metal and non-metal come together, it's most likely to form ionic bond because of that. Okay, all right, so yeah, so as I mentioned, right, so if you have non-metal and non-metal combined, it's most likely to form ionic bond. But if you have non-metal and non-metal, the difference in En are slightly different, so they are going to sharing electron, they will not transfer electron. So that's the cause of the two different type bonds. Okay. All right, so I have example here. We are going to use the En value to predict the type bonds for all of these. Okay, and also we're gonna look at which one have the greatest degree of polarity, which means which one is going to have the biggest difference, right, between the En value of the two atoms. And we are going to list out as well what type of bond are these. Okay, so I'm going to start with magnesium and fluoride. Okay, so pretty much if you're looking at the value, magnesium is right here, fluorine is right here. Okay, so you're going to do 4 minus 1.2. Again, if you do 1.2 minus 4, make sure that you actually get the positive value of it, right, because the delta En have to be the absolute value for this. Okay, and again, the difference of this is 2.8 is indicate so is indicate the ionic bond, right? So it's greater than 2. So we're gonna look at that later. Okay, so I want you to keep doing for bromine and chromium, oxygen, carbon, chlorine, and oxygen, phosphorus. Okay, so let's do those. Okay, so I got the bromine equal to 0 for the delta En. Chromium, oxygen, I got 1.9. Okay. Carbon, chlorine, I got 0.5, and then oxygen, phosphorus, I got 1.4. Okay, so these are the difference in En value. So clearly, the greatest degree of polarity would be magnesium and fluoride, right, because it have the highest value of the En difference. Okay, so if you're looking at this scale right here, okay, so you can use this scale to tell us what type bond. Okay, so this is what we're gonna do. Okay, so because greater than 2, it would be ionic bond. Okay, so between bromine, 0, that would be non-polar covalent. Okay, chromium, oxygen, 1.9, that would be polar covalent. Okay, carbon and chlorine, that would be polar covalent. Okay, oxygen and phosphorus, that would be polar covalent also. Okay, so because magnesium fluorine is the ionic bond, you can also identify the charge as well, right? So because fluorine has the highest En compared to magnesium, so fluorine would be the one that get a negative charge, and magnesium would get a positive charge because fluorine would withdraw electron completely away from the magnesium, right? So these two are full charges. Okay, now I can skip this because they are sharing electron equally. Okay, so they're not creating any charges. But between chromium and oxygen, they are going to create partial charge, where the oxygen has higher ability to withdraw electron according to its En value, right? So En value of oxygen is 3.5, En value of chromium is 1.6. So oxygen would be the one that it would be assigned as partial negative, and chromium would be the one that assigned as partial positive, because oxygen is going to pull electron away from chromium, is going to share electron unequally in this case. Okay, now same thing for carbon and chlorine as well. Chlorine is 3, right? Carbon is 2.5. Therefore, partial negative would go to chlorine, and partial positive would go to carbon. Okay, Between oxygen and phosphorus, oxygen is 3.5, phosphorus is 2.1. So clearly oxygen has higher ability to withdraw electrons. So oxygen would get partial negative and phosphorus would get partial positive. Okay. So another way to tell about polarity or the direction of how electron is being withdrawn is by using a dipole moment. Okay, so a dipole moment is a measure of the separation of the positive and negative charges. Okay, so between this, right? So the arrow is what we are going to use, right? So this arrow right here indicates the dipole moment. The head of arrow will go toward the one that is able to pull electron the most, which means the one that have higher En value. For example, in this case, between chromium and oxygen, the arrow is going to go toward oxygen. It's indicated the electron is going to pull toward oxygen more. Same thing for carbon and chlorine as well. The head of arrow will go toward chlorine, indicating that the dipole moment the charges will go toward chlorine. Okay. For oxygen and phosphorus, okay, so since oxygen has higher En value, the arrow will go toward oxygen, indicating that that is the direction of how electron is being pulled. Okay. We are not going to use the dipole moment for the ionic bond because these charges are already they are full charge. They are not partial. They already completely transfer electron. Okay, so the dipole moment or partial charges only used for the polar covalent compound. All right. So the last part of this lecture that we are going to take a look at is we are going to take a look at the different type of the classification of matter in terms of like atomic element, molecular element, and also compound as well. Okay, so atomic elements are those elements that contain one single atom as an element. And as you already see, one of them would be isolated atom, right? So all of these noble gases, they are going to present as atomic element in nature. Okay. All those metal, even though they are present as a group of metal, right, according to the metallic bonding, we are still going to consider these atomic elements because they are containing of only one type of element. Okay, so these are still going to consider to be atomic element. For example, if I talk about potassium, we can consider that potassium as atomic element, right? If I talk about copper, we can consider copper as atomic element. Molecular elements are the elements that contain two or more atoms of the same element bond together. And this is something that you will need to know. So the diatomic molecules are these type of element that they are going to be present as two atoms in the in nature. For example, if we talk about hydrogen gas, you will need to know that it's going to contain two hydrogen for that molecule, right? So if we talk about oxygen gas or oxygen element, you will need to know that it's going to come as O2. Okay, so these are the list of the diatomic molecules that you will need to know, okay, for each of these elements. So in order to memorize these, there are two ways to memorize it. Is either it look like a number 7, right? So you can memorize like that. Or another way to remember this is that there is a saying say that have no fear of ice cold beer, right? So have is for hydrogen, no is nitrogen, right? Fear is fluorine, of is oxygen, right? Ice is I, right? Cold beer would be chlorine and bromine. Okay, so note that cold beer is not carbon and bromine, right? So it's boron and carbon. Okay, so cold beer would be chlorine and bromine because in group 7A. Okay, so make sure that you actually memorize that correctly. Okay, so this is what you have to know. Okay, so when I talk about the element that present as a diatomic molecule, you will need to know those are these element right here. And there are other type of elements as well that contain more than 2 atoms that bond together in a molecule, and those are such as phosphorus and sulfur. Okay, so these are what we refer as polyatomic molecule. Poly means many, right? So it's many atoms in a molecule. Okay, but what you need to know is only the list of the diatomic molecules, because you are going to see this more often later on in for the rest of this term and also for the following terms as well. Okay, and so the reason why these atoms are bound together as molecules, again, because they want to achieve the electron configuration as the noble gas, right? They are more stable to share electron between each other for that. Okay, So when we talk about compound, okay, so when we talk about compounds, you already see that the first type is molecular compound. So these are containing the atoms from nonmetals and nonmetals, or sometimes nonmetals and metalloids, right? They are going to have to combine in a fixed ratio. Okay, so we already talked about this. Okay, so pretty much you are going to have two different type of nonmetals or nonmetal and metalloid combined in order to form ionic molecular compound. Sorry. And the bond in the molecular compound we already learned, right? So it's going to be covalent bond because they are sharing electron. Okay, so the last thing or the last compound that we look at is the ionic compound. So this is come mainly from the metal and non-metal combined, okay, in a fixed ratio. And because metal loses electron to non-metal, therefore we can also call metal as cation and non-metal as anion as well. And these are the combination between those two. Okay, so pretty much what we learn, if you put this in terms of classification of element and compound, you can say that if you have a substance, right, you can either classify it as element or as a compound. Element would be the same type of element. Okay, compound would have two or more type of element. Okay, for element, you can also differentiate as atomic element or molecular element. Atomic element are those that are going to be by itself in nature, right? Molecular element would be those elements that are going to be in form of molecule in nature. For example, oxygen, it would be present as oxygen molecule in nature. For compound that contain two different type of elements, you are going to be able to get classify this either as molecular compound or ionic compound. Molecular compound would be the one that are sharing electrons, so would be non-metal and non-metal, and ionic compound would be metal and non-metal. Okay, so here is a quick review of those definitions, right? So for example, sulfur S subscript 8 in this case is contain only one type of element, but it's come as many atoms, so this would consider to be molecular element, right? K3PO4, we have metal and non-metal, so this would be an example of ionic compound. Okay, lead, okay, so just one single element in this case, so it would be an example of atomic element. NH3, right, so both elements are non-metal, so this is an example of molecular compound. So here is the review of what we learned in this lecture video. Start working on your homework, chapter 5.1.